Look at the crazy chart. Talk a little bit about this. So here are some examples of the things we're going to graph and what they would look like. So see how they all look kind of different? Like this is kind of weird. Like this one almost looks like a horizontal line, but it has this curve happening in the middle. This one looks like a regular line, except for that it has a hole in it. Okay, there's like one point missing from the line. Kind of weird, right? And then this one's more like what I just showed you. It's got these like guidelines here and the functions there. And it could fall into any of these categories, okay? So again, for us to figure that out, we want to look at the equation. We're going to use our factoring skills because we want to be able to factor the equation in order to find out all of these things right here. So notice the first three things listed: vertical asymptotes, horizontal asymptotes, oblique asymptotes. How many of you guys have heard of vertical asymptotes before? I know it's taught in Algebra 2. In Algebra 2, you learned how to do some stuff like this, right? Okay. It just depends on how much you remember, all right? Horizontal asymptotes, how many of us have heard of those? That existed in Algebra 2 as well. Oblique asymptotes, how many of us have heard of those? Like a couple of us. We definitely didn't address that in any regular Algebra 2 classes, okay? So that if you haven't heard of it, that's the reason why you weren't supposed to have heard of it, okay? And if you have heard of it, good, okay? X and Y-intercepts, we have found before. Branches are just ways for us to describe parts of the graphs, because now that the graphs are like separated in certain sections, we don't say the first graph and the second graph because they're all part of one graph. So instead we say like this branch of the graph and this branch of the graph. And the graph could have lots of different branches depending on how many places it's kind of split apart. Okay. If it's split apart, we don't keep saying that word in math. I'm saying that because I feel like it's understandable, but we call it continuous or discontinuous. So this first graph up here is continuous. I could put my pencil on this graph and draw the whole thing without ever lifting up my pencil. Okay? Well, let me skip to the third one. The third one is discontinuous. Okay? So I could draw this, but it doesn't connect to the other branch, so I'd have to lift up my pencil to go draw that one. The middle graph is technically discontinuous too, but I know some of you are going to say like, well, I could just go like this, Miss Dahl, and I could put my pencil like that, and I could just keep going. Right. Okay, but really, why is this open circle here? Because a hole is missing from the line. That's just the way we note it. But really, if you like graphed it on a graphing calculator, it's not going to draw a little open circle for you. It's just going to have a line, and then all of a sudden it's going to be missing a point, and then the line will continue. Okay, so it's a discontinuous as well. Okay. So this one is what we call a hole or a point of discontinuity, and then we'll talk about the removable and non-removable part. But just so that you know where we're headed as far as vocab. So this is a lot of stuff, but it's a lot of stuff because if you can find all this stuff out, you can get a graph like that without having to plug in a million points. Okay? So then our question becomes, how do we find all of these things? And that's what we're going to focus on today. So notice the behaviors at the ends of the graph. Okay? This graph behaves almost like this straight line at the end, and same thing on the other side. Okay? This graph is similar, even though the branches are completely separate, the ends start behaving like this straight line right here. Okay? Those graphs both have horizontal asymptotes. Okay? They have lines that at the ends look horizontal and your graph starts following them. This graph in the middle doesn't have a horizontal asymptote. It behaves like a line at the end, but not like a horizontal line. Okay? This side shoots up towards infinity, and this side shoots down towards negative infinity. So the chart that you guys have, we're going to use it to look at end behavior. So I know it's kind of crazy. Let me show you how it works, and then we'll use it to answer some of the questions. So be thankful. One year I made people fill out all the numbers in the chart. Okay? Now I don't do that anymore. It's not really a good use of our time. Okay? But basically, all the chart is this. This is a function, okay, like the new types of functions we're going to be graphing. Then what they did is they basically made an XY chart for each function. The X values stayed the same that they plugged in every time, and you can see them at the top. They plugged in negative 1,000, negative 100, negative 10, negative 1, 0, 1, 10, 100, 1,000. Okay? Then notice there's like some weird notation at the end. It says like the limit as x goes to infinity of f of x. Basically what that means is what's going to happen when you plug in bigger and bigger x values? If you kept plugging in bigger numbers past 1,000, you then plugged in 10,000, a million, right, 100 million, whatever. What's happening? Is the graph going towards one number that it's basically going to stay at? Or is the graph shooting up towards infinity or going down towards negative infinity? So we want to look at the numbers that they got by plugging stuff in and make a decision about what's going to keep happening there, okay? And then same thing on the other side. Okay? So we'll do a couple together, and then we're going to let you guys work in your groups and try to answer some of the questions that are in the note guide. Okay? All right, so notice that the paper's kind of split up. There's like the top 4 equations, the middle 4, and the bottom 4. There's a reason for doing that. Okay, so here are the top 4 equations in the chart. So to look at the end behavior happening towards the ends of the graph, we'll do one together so that we can understand how this is working. So let's look at this second one right here. Okay. So let's say as we start plugging in really big x's, okay, we just start moving down the x-axis, plugging stuff in, we want to look at what's happening to the y values. Okay. So negative 0.5, 0, negative 0.5, negative 50, negative 5,000, negative 500,000. Okay? So based on the evidence that you see, if you kept plugging in more and more numbers, what do you expect to happen? Do you expect the end of this graph to be horizontal and just like hanging out by the number 4 or something? Or do you expect it to be shooting up towards infinity because the y values just keep getting larger and larger? Or shooting down towards negative infinity because these y values keep getting smaller and smaller? So what do you guys think based on those numbers? So the numbers went from negative 0.5, negative 50, negative 5,000, negative 500,000. What do you expect? Are you seeing it even out and kind of settle down at one number? No. Are the numbers getting infinitely large or infinitely small? Small because they're negatives, right? So what we would say is since it's not settling down at a number, it's either shooting up towards infinity or shooting down towards negative infinity, right? And since these are negative, I would say, okay, at this end, this graph is going down towards negative infinity. So if I was graphing this picture, there might be all kinds of crazy stuff happening in the middle. But as you got towards the end, I would expect the graph to just keep plunging downward. Okay? What about at the other end of the graph? Okay? So as we start plugging in negative x values, what's happening to the y values? So 0, negative 0.5, negative 50, negative 5,000, negative 50,000. So what's happening as we look this way? Is it settling down at a number? Is it shooting upwards towards large positive numbers or downwards towards really negative numbers? Again, the same pattern, right? That's happening. So down towards negative numbers. So this would be, again, like down towards negative infinity. Yeah, I know.
So does that graph just look like one line that's going down?
It wouldn't look like a line.
I mean, like a little.
Well, right. So it could have. We don't really know what's happening in the middle. We have some points, but we don't know if stuff's happening in between them. So we don't know anything about what's happening in the middle of the graph. All we have established is at the ends of the graph, they both are shooting downward. So this could just go like this. This could go like this. Okay? So we're just kind of establishing at the ends. We'll find other ways to figure out what's happening in between everything. This first investigation is just like, how do we know how to end our graph? Okay? In the next set of equations, you guys will answer the questions in your group. So here's the next set of equations. Okay? Let's look at the third one in that group. All right, so look at what happens as we plug in positive x values. So we go from positive 1.8 to negative 14, back up to positive 1.1, then to 0.3112, negative 0.3324, negative 0.3333. So does this one seem to be getting drastically larger, drastically smaller, or kind of staying around one number? So look at these last two things. Yeah, like, did these get very different? No, and this is what they got when they plugged in 100, and this is what they got when they plugged in 1,000. They plugged in a much larger number, but did they get anything that's much different than what they got? No. So it seems to just start hovering around this number, right? What number do you think it's hovering around? 0.333333. Okay, so I'm going to write it as a fraction. So that would be negative 1/3, right? Okay, and if we look at the other end, so same thing from 1.1 to negative 14 to 1.8 to negative 0.3254, negative 0.3339, negative 0.3334. So again, these numbers are really close together, even though we're changing drastically the x value that we're plugging in. So again, it seems like these are just kind of hovering around that negative 0.333 space. Okay. So negative 1/3. They won't always be the same on each end. Okay, they could be different, but this is what we're seeing here. Okay? We're going to do one more, and then we're going to let you guys work together. All right, so this is the last set of equations that are there. Okay, and let's see. We'll look at the first one in the set. All right, so negative 2.5, negative 2.667, negative 2.8, negative 8. Okay, so we're just kind of plunging down. But then 0.47059, 0.04061. What would you kind of expect the next output to be if I plugged in something like 10,000 or something? 0.004 or something, right? That's kind of the pattern that we see, like, 0.4, 0.04, 0.0004, eventually 0.0000000, right, way out there. So what is this getting closer and closer to? If you had a number like this, if you plugged in something really big and you got all these zeros before you got, like, your 4, what number is this really? What would you round this to if you got this as an answer? 0, right? So essentially it's like this is starting to look like 0. Okay, so I see that it's not bouncing very far, and I see that the decimal is kind of moving away from that, giving me that pattern. I would say it's getting closer to 0. Okay? And when we look at the other side, negative 2.667, negative 2. Negative 1.6, negative 0.34, negative 0.034. So again, I'm kind of thinking like, I'm going to get like negative 0.00000, right? So if you do this, eventually, okay, no matter what number's out here, right, what would you round this to? Negative 1? 0, right? It's like almost 0, right? There's nothing here to make this up to 1 yet. I know we want to say 0. All right, so those are the end behaviors that we're looking at. We're just looking at the y values in the chart and saying, as they start plugging things in, it kind of settles down, and it's settling down close to this number. Or it's not settling down, which means it just keeps getting big towards infinity, or really negative towards negative infinity. Okay? Everybody kind of understand? Okay, so in your group, it looks like most people heeded the advice and got the printout, so you should have a copy of the chart. If it's your own copy of the chart, you can fill it all in. If you don't, I have a class set. I don't know how many are left of my class set. But there's probably at least enough for every group to look at it. But if it's my class set, don't fill it in, okay? But what you want to use it for is to answer the following questions. So after each set of the chart, so like here's the first set of 4 equations, you want to answer these questions in your note guide. In each of the first 4 equations, what is a true statement you can make about the degree of the numerator compared to the degree of the denominator? Do you guys remember what degree is? So if I write this like x3 plus 2x plus 1, this is a polynomial. What is the degree of this polynomial? 3, okay? Each term has its own degree. This term has a degree of 0. This term has a degree of 1. This term has a degree of 3. But the degree of the whole polynomial is just the highest one. Okay, so this has a degree of 3. So you're going to look at those first 4 sections and what the crazy equations look like, and you're going to tell me something you can say is true about the degree of the numerator, the top, compared to the degree of the denominator. Okay? And then based on the limits that you found in the chart, don't be scared of the word limits. Those are the numbers you filled in at the end, right? You're saying it's going towards these. Can you tell me something about all of these kinds of equations, what you see happening at their ends? And then would you expect then there to be one of those horizontal asymptotes that it follows at the end? Okay? And then you're going to go to the second group of equations, those same exact questions for the second group of equations, the third group of equations, and the same exact questions for the third group of equations. Is this okay with everybody? Okay? So you kind of get the gist of how to find the end behavior since we did a couple together. So use your group, look at the first 4, go answer those questions. Look at the second 4, go answer those questions. There's also like a class set of a copy of the questions on the side. So if you don't have the note guide, use your notes on your own paper, but you have the questions to guide you over there. Okay, don't write on it because I need it for the other class, and my Algebra 2 Trig class is doing similar stuff right now, so they're using some of those questions as well. So I definitely need it in class, but you can use it so that you can have something to look at while you're writing down the answers. Okay? Any questions before you start working with your group? Yeah, Kendall?
So when the numbers are getting like exponentially smaller or larger on both sides, it's pretty steady. That's negative infinity and infinity.
Right, when you see like big jumps like 50 to 500 to 5,000, it's not settling down at all. Yeah. Okay. Okay, I know you might not be done, but I want to make sure we all have correct information on our paper so that we have a chance to go through it as well as think about it. And some of you are just like plowing through and doing an awesome job. Okay? Some of you got stuck at certain spots, and that's okay. We'll clarify. Can anybody give me what they got as the end behaviors for this first equation in the section of first 4? Kendall? And on this side? Okay, and what about the third equation in this section? Go. And on this side? Good. Cool. All right, and the last one? Yeah. Good. Okay, so none of these functions in this section of the handout kind of settle down to one number. At the ends of all of these functions, they are either increasing towards infinity or decreasing towards negative infinity. Okay? So then there were some questions that we answered about these. A, in each of these first 4 equations, what's a true statement you can make about the degree of the numerator compared to the degree of the denominator? So what did you guys figure out? John? Good. So in this first section of equations, the numerator has a greater degree than the denominator. Okay? That's going to be important to you because remember what we're trying to figure out. Eventually, someone's going to put an equation like this in front of you, and you're going to have to graph it. So this first investigation that we're looking at is, okay, we'll do some other things to figure out what's happening kind of in the body in the middle of the function. But tell me how my function's supposed to end. How am I going to know just by looking at the equation how it's going to end? Well, now we know that if you're in this category where your numerator has a greater degree than your denominator, what did you guys see happening at the end? So for part B, based on the limits, what's your conjecture about, okay, if you have this kind of function, what's it going to behave like at the ends? So what do you guys think? Yeah, so good. End behavior goes toward infinity or negative infinity. We saw both happen, and sometimes they were the same, and sometimes they were different, okay? So in these functions, they don't settle down. You would expect at the ends, and that doesn't mean you're going straight up. It could curve like a parabola, it could travel like a line, but it's still traveling up forever on one end or down forever depending on what you get, okay? So would you expect these kinds of functions to have a horizontal asymptote? Would you expect them to follow a horizontal line at the end? No, you just said they're shooting up or down towards negative or positive infinity, right? So are they following a horizontal line? No, they might follow some other shape, like a parabola or some other line, but definitely not a horizontal one, okay? So I would not expect a horizontal asymptote. And the reason, basically, I'm going to just refer back to what we said previously, because the ends are either going towards infinity or negative infinity. They're not settling down towards one number. Okay? So are we okay with this first set of 4 equations? So now you don't know very much else, but you know if someone put an equation like this in front of you and you saw the numerator had higher degree than the denominator, you wouldn't expect a horizontal asymptote, and you would expect the ends of your function to either continue to grow like a parabola or like a line or a cubic or something towards infinity or negative infinity at the very end. Okay? All right, so second set of functions that we looked at. Can somebody give me what you got as end behaviors for the first one in this group? Huh? 2 and 2. Good. All right, and for the second one in this group, what did you guys get? 4. Oh, for this one, what did you get? 4.2. Good, 0.2. That's also 1/5. I'm just going to write this here because it's going to help us later. And then you should see that same thing happening at this end. All right, and what about the last equation in this group? What did you guys get for the end behaviors? 4. So this is much different than the previous group, right? Okay. These aren't shooting off towards infinity or negative infinity, but they're also not very consistent. Every function kind of had something else that it was doing. Okay. So when you guys looked at the equations that were there, somebody raise your hand and tell me what can you conclude about the degree of the numerator and the degree of the denominator in this group of functions? Oops. Good. Okay. So the degree of the numerator equals the degree of the denominator. So if you look at all of those equations, they all have the same highest power of x in the numerator and in the denominator. So if the equation that someone had put in front of you was like this, you would think of it differently than if the numerator had a higher degree, because we saw something different happen at the ends, okay? So based on what you did see in the chart, what would you say about the ends of graphs that fall into this category? If you get one where the numerator and denominator have the same degree, what do you expect to see at the ends of your graph? The same on each side, okay? And towards infinity and negative infinity, or towards one number? Look back at all the equations. None of them went towards infinity or negative infinity, right? They all had the same number that they approached at the beginning and end. They didn't, all the different functions didn't go to the same number, but each individual function had the same number as the end behavior on each end, okay? So we would say that we would expect approaches the same value at both ends. Okay. So would you expect a horizontal asymptote for these types of functions? Okay. Would you expect them to follow some horizontal lines at the end? Yeah. Okay. Different for each one, right? Like if I go back, this one I expect to follow a horizontal line at 2. This one I expect to follow a horizontal line at 0.2, etc. But I would expect a horizontal asymptote. So the answer here would be yes, and it's because of what we said here. The end behavior has the same value at each of the ends, so it's just kind of hanging out at this one number. It's not exactly that one number. You saw the numbers, right? It never exactly reached it, but it's getting like infinitely closer without ever reaching it. Kind of weird, okay? But it's like the fact that there are infinitely many numbers between 0 and 1. So you could keep getting closer to 1 without ever actually getting to 1. Kind of, okay? All right, so the last section. What did you guys, who can tell me what they got for end behaviors in this section? You? Oh, it's telling me, just like that. Zeros, okay? So on these ends, we saw them each approach 0. On these ends, we saw them each approach 0. Okay? So I don't know. This might be the most friendly section of equations, right? Okay. So what's true about the degree of the numerator compared to the degree of the denominator for all those equations that were in that final section? What's that, Lila? The less. Good. Okay. So the degree of the numerator is less than the degree of the denominator. Okay? All right, so based on what you saw in the chart, what is your expectation for end behavior if someone puts in front of you a function that has this characteristic, that the numerator has a smaller degree than the denominator? Where do you expect your function to do at the ends? Look at your chart. What did all of those functions do at the ends? They got really close to 0, right? Okay. So both ends approach 0. And again, I'm using the word approach 0 because they didn't technically equal 0, but they're getting infinitely close to it. Okay. So would you expect these kinds of functions to have a horizontal asymptote? Are they hanging out at one specific value at both ends? Yeah. Okay. So yes, we would. And again, why? Because both of the ends approach a single number. And in this case, we know the single number. It's specifically at 0. Okay. All right. Okay, so we'll come back and we'll finish this other part of it on Monday. Okay. We'll kind of make our conclusions. But make sure you have written down those summaries. Okay.